Good afternoon, everyone, and welcome to our 7th Infogest Viva webinar. My name is Talita Comunian, and I will be starting this webinar. I'd like to introduce Ever Hernandez and Daniela Freitas, who will conduct the webinar. Good afternoon, everyone, and welcome to our 7th Infogest Viva webinar. Sorry for the mistake. So I would like to introduce Ever Hernandez and Daniela Freitas, who will conduct the webinar together with me. This event is organized by a team of postdocs in the Food Research Center of Moorpark, Chagas. The goal of this webinar is to provide you the most recent findings in the field of digestion with presentations from the most recently graduated PhDs. This webinar is broadcasted live on YouTube and will be available soon in the Infogest YouTube channel. The recorded presentation will be followed by a Q&A session with the speaker, so I'm inviting you to use the Q&A button to ask your question. Now, I'm going to introduce our speaker, Marcus Infantes-Garcia. Marcus did his PhD with Professor Tara Grauwet at KU Leuven in Belgium, and his project title is From Gastric to Small Intestinal Lipid Digestion, the role of oil in water emulsion designed to affect in vitro lipolysis kinetics. Marcus, the floor is yours. I'm going to share your video.
Dear attendees, welcome to this Infogest webinar session. My name is Marcos Infantes. I used to work in the Laboratory of Food Technology at KU Leuven, Belgium, and today I will present you some interesting findings of my research regarding the impact of emulsion design properties on gastric and small intestinal lipid digestion kinetics under in vitro digestion conditions. So let's start with this slide. It says, let food be diet medicine and medicine be diet food. This was a phrase stated by Hippocrates 400 years before Christ. And this phrase is linked to the fact that food can have diverse health implications. So we know that foods contain macro and micronutrients. If we talk about macronutrients, lipids are one of the main macronutrients present in foods, and they can be ingested as a bulk or as emulsions. And these lipids, they can have, as I mentioned to you, different health implications. So, for example, we know that the maximum we should ingest 30% of lipids as a total caloric intake. Otherwise, we will be in risk of suffering from some metabolic-related diseases. But on the other side, on the positive side, we can also use lipids to induce some physiological responses in our bodies. So, for example, we know that a high rate of release of lipid digestion inside our gastrointestinal tract could be useful, for example, in some population groups like infants or of elderly, to supply them with some essential nutrients or bioactives which are incorporated in the lipids. On the other side, for instance, a slow rate of release of lipid digestion or of lipids could be used to induce satiety or a prolonged satiety effect in obese people, for example. So here we have the two sides of ingesting lipids. And for example, in case of these positive aspects, we know based on previous studies that by designing emulsion properties, for example, or we can induce this specific high or slow rate of lipid digestion, and actually we can design these emulsion properties by formulation or processing from a food science perspective in order to have a tailored functionality. So how can we modulate lipid digestion by emulsion design? For example, we know that an important emulsion property is the droplet size because it affects the surface area for lipase absorption. Then the interface is also quite important because the chemical nature and the type of compound which is absorbed to the interface will affect the absorption of lipase to the interface. Also, the lipid phase is quite important, depending if it's a saturated or unsaturated fatty acids that compose the triglycerols in the oil droplets. They can have a different effect on lipid digestion. Also, the aqueous phase compounds, they can, for example, interact with the digestive elements like bile salts, or they can also increase the viscosity, or they can form gels even. So this will also affect the lipid digestion kinetics. Based on previous studies, we have observed that most of these emulsion properties have been studied in the small intestinal phase with different in vitro methods, so testing using diverse physiological conditions. Then in other studies, we have also observed that some of them report endpoint measurements, so they don't focus on the kinetics. And in the previous slide, I have shown you that the kinetics are really important. So understanding them is important to know how to tailor some functionalities inside our body. Also, in some previous studies, one response is normally reported. In many studies, we see that free fatty acid release by titration is commonly reported. And then there is also quite limited information on gastric lipolysis. There are only few studies on this. And also the interfacial changes during gastric digestion, especially, are scarce in previous studies. So that's why today I would like to mainly focus on the gastric phase. I will also show you some results on the small intestinal phase. And in this case, due to time constraints, I would like to focus on one emulsion property, specifically on the interfacial composition, and see how we can affect gastric and small intestinal lipid digestion kinetics from a food design perspective. Then a second objective is also was to elucidate the molecular mechanism, in this case of gastric lipolysis under in vitro digestion conditions. Before showing you some results, well, this is actually already some results we obtained in an early study in which we subjected emulsions prepared with single emulsifiers or single stabilizing agents. So in this case, we produced 5 emulsions that were subjected to in vitro gastric digestion. And in this graph, it is shown the evolution of digested triolein during in vitro gastric digestion. And here I am highlighting 2 emulsions. So one stabilized by citrus pectin, the other one stabilized by Drouin 80, and they show really distinct digestion kinetics. You see the citrus pectin emulsion was digested quite fast and also very extensively, as compared to the Drouin 80 emulsion, which show really negligible lipid digestion. So based on these results, we were actually interested in understanding better what would happen if we mix these 2 emulsifiers to form a mixed interfacial composition, and see what is the effect, first of all, on the emulsion stability, but also more important for us to evaluate the effect on lipid digestion kinetics, and see if we could tailor lipid digestion kinetics by mixing 1% of citrus pectin and different concentrations of Drouin 80, because Drouin 80 we know is a an emulsifier with high surface activity, which normally blocks gastric lipase absorption. So in terms of physical stability, we see here that the initial samples, all of them had a particle size diameter, an average one around 2 micrometers. And then during digestion, this particle size increased slightly. We obtained particle sizes ranging from 3 to 8 micrometers, and especially the emulsions containing higher 280 concentrations, they show better stability. So the particle size was almost the same before and after 2 hours of gastric digestion. We also characterize the zeta potential. And here I put this graph because we obtain interesting results. So here you see the 5 emulsions, all of them contain 1% of pectin, but different 280 concentrations, as I showed you before. And in this case, we see that as we decrease the concentration of 280 is an emulsifier with a non-charged emulsifier, and pectin normally shows a negative zeta potential. So we see that as we decrease the concentration of 280, we observe a more negative zeta potential, which could be linked to a higher interfacial concentration of pectin. And actually, this is more or less what is explained here. So at high 280 concentrations, we probably have higher extent of pectin desorption from the interface. So it was displaced at a higher degree as compared to the low 280 concentration in which more pectin was absorbed to the interface after being mixed with 280. Then having a look to the gastric lipid digestion behavior, in this graph again, we observe the evolution of digestive triolein along the gastric phase. And here we observe quite interesting results. So we see that these emulsions with low 280 concentrations, so these ones I'm referring to these two, they resulted in very fast and extended lipid digestion kinetics. And as we increase the 280 concentration, these kinetics are slowed down, and also the extent of lipid digestion is smaller or is lower. And this is more clearly observed in this table. We have the 3 kinetic parameters. So the lag phase, which was smaller for lower 280 concentrations, the reaction rate constant, which was larger as we decrease the concentration of 280, and the extent, as we also see here in the graph, it was higher for lower 280 concentrations. Then a possible explanation for this behavior is that when we have high percentages of 280 over a high percentage of hydrolysis or lipid hydrolysis, so this is for low 280 concentration emulsions, we observe no lag phase. In this case, we probably had more pectin absorbed to the interface, and we know that pectin allows gastric lipase absorption, so leading to faster and also more extended lipid digestion kinetics. And then in this other case, when we have low lipid digestion hydrolysis, we observe a more extended lag phase, and this is because probably 280 was present in a higher concentration at the interface, so gastric lipase absorption was blocked by these 280 molecules. This is just hypothetical. But in a later stage, during my research, we proved this hypothesis, and I will show you some results on that later on. Then we also subjected these samples to the small intestinal phase, and in this case, we only chose 3 emulsions. So two of them with the extreme 280 concentrations and an intermediate level of 280 concentration as well. What we observe here in this graph is that when we have higher 280 concentrations, also the initial digested triolein is lower. But then this emulsion showed the highest stability during the gastric phase. So that's why, well, in this case, the particle size was smaller. And then this one showed really fast digestion kinetics as compared, for example, to this other curve in which the 280 concentration was smaller. And even if the digested triolein was higher at the beginning of the small intestinal phase, the kinetics were slower. And in this other graph, it is clearly shown that there is a link between the droplet size and the rate constant and the reaction rate constant. So we see a negative relation between them. So the higher the droplet size, the slower the reaction rate constant is. So slower kinetics for higher droplet size. So as a summary of these results, in the gastric phase, we could modulate lipid digestion kinetics by mixing pectin and 280 at different concentrations. Then in the small intestinal phase, we observed that emulsion stability was playing a major role affecting the kinetics in this phase. So here the droplet size was the most important factor affecting lipid digestion kinetics. Something interesting to notice, especially in the gastric phase, is that this modulation could be a starting point to design emulsions for tailored lipid digestion. With a tailored lipid digestion, for example, to influence satiety satiation or to deliver some functional compounds. And in this case, I use or we employ pectin to prepare the emulsion. So pectin, which is also a novel ingredient. So it confirms that this pectin has some emulsion capacity to form these to form emulsified systems for sure. So this could be included also in future studies. But then we had a question about what was the mechanism behind this modulation. So we went to the next phase of the study in which we check also the interfacial tension kinetics and also the dilatation biology of these emulsions. So we use a pendant drop technique using the octopus system, which was developed in the University of Granada. And in this case, we chose 4 systems. So two systems stabilized by a single emulsifier, so pectin and 280, and 2 other stabilized by the 2 emulsifiers. So here we form mixed interfacial layers. Then in this slide, I show you the formation of the single interfaces. So interfaces formed in this case by citrus pectin. We see the decrease in interfacial tension. So it shows the absorption of citrus pectin. So it confirms the interfacial activity of citrus pectin. And then this part is the desorption. And in this case, we observe that this pectin form a highly interconnected network, which show a high elastic modulus. So this high elastic modulus can be explained by the intermolecular interactions between the pectin molecules. Then for the 280 system, we observe also a quite fast decrease in the interfacial tension. So if we compare these two, we see that the 280 is more surface active than the pectin for sure. It's a smaller molecule with higher surface activity. And then the rheology analysis also show us, so at the end we observe the rheology analysis and we see that this 280 film was fluid and with a low elastic modulus. So it was a rigid and fluid interfacial film. Then we subjected these two single interfacial layers to in vitro gastric digestion in the same equipment, so independent drop equipment. And then here we observe that, yeah, this is the formation of the pectin interfacial layer, and this is the digestion of the interfacial layer. You see the conditions here. And we see a fast decrease of the interfacial tension, which reflects the production of lipolysis products, which also are surface active, like for example, free fatty acids, monoglycerols and diglycerols. They are surface active. And this is a scheme representing the digestion process at the interface. So displacement of pectin molecules, most likely absorption of gastric lipase and production of lipolysis products. On the other hand, the Drouin 80 system, it show almost no change in interfacial tension during digestion. So it reflects the blockage of gastric lipase absorption and also no production of lipolysis products, which also correlates nicely with the in vitro digestion experiments that we performed before. So very fast kinetics for the pectin emulsion and also negligible lipid digestion for the Drouin 80 system, let's say. Then about the mixed interfacial composition, we first formed the interface by pectin absorption, then followed by we then added Drouin 80 at 0.1% in this case, and we see a fast decrease in the interfacial tension, which reflects the absorption of Drouin 80. So in this case, we can interpret this as a high degree of displacement of pectin from the interface. We show also a low, and this is because we observe a low elastic modulus. So we can compare this elastic modulus to the single Drouin 80 interfacial layer. So that's why we in this graph we explain the desorption of pectin by the rheology analysis. And then for the system in which pectin or Drouin 80 was added at a lower concentration, we see almost a very slight decrease in the interfacial tension. And also the rheology analysis that you see here in the end shows a high elastic modulus. So pectin was most likely still absorbed to the interface, but a bit compressed by some Drouin 80 molecules absorption. Then after subjecting these mixed interfacial layers to in vitro gastric digestion, in the case of the higher Drouin 80 concentration, we see a slight decrease in the interfacial tension, so really limited gastric lipase absorption and also production of lipid digestion products, and for sure desorption of pectin molecules. While in the other case, in which we have a smaller Drouin 80 concentrations, the digestion shows a more pronounced decrease in the tension, which reflects a more extended gastric lipase absorption and also a higher production of Drouin 80. But I think in this case, this graph should be the other way around, sorry. So this one should come here. And this behavior is also correlated nicely with what we observe in the in vitro digestion experiments. So higher faster kinetics, more extended kinetics for the lower Drouin 80 concentration, while slower and less extended kinetics for the higher Drouin 80 concentration. So this is a summary of our observations. So here we can conclude the competitive absorption was playing a role in the modulation of in vitro gastric digestion for these mixed interfacial systems or mixed interfacial composition emulsions. So as we increase the Drouin 80 concentration, we observed that a lower gastric lipase absorption degree and also lower production of lipolysis products. And we also observed a nice correlation between the digestion of the emulsions in the in vitro digestion experiments and also independent drop equipment. So the next research objective in my project was also having a look to the lipid digestion mechanism. And in this case, I will show you results on the gastric phase only. So for this purpose, we employed an advanced statistical technique called multi-response modeling. And this technique starts with the literature search. And also we need to have a look to our own data to see some trends with the different responses that we have measured. Then based on this, we propose a reaction scheme. So in this case, we have proposed this one with enzymatic and also isomerization reactions based on literature and also based on our own data. Then these reactions are transformed into differential equations that are further solved by numerical methods. And then in the end, we obtain our mechanistic model. In this case, this reaction scheme produce differential equations that converge with the data sets that we introduce in the modeling process. So actually, this reaction scheme fitted, but then this is an iterative process. So in the first attempt, you won't obtain a convergence of the model and also a good statistical parameters that confirm that this is the final mechanistic model. So normally this process takes some time, so you need to test different reaction schemes. But the one I'm showing you in this slide is the final one. So after several attempts, and this reaction scheme consists of 7 reactions. As I mentioned to you, 5 of them are enzymatic reactions and 2 of them isomerization reactions. And then based on this reaction scheme, we can also generate models like to predict or to estimate or to model in this case the evolution of the different lipolysis products. In this case, we quantified regioisomers of the olein and monolein. We quantified also the final product oleic acid, so different intermediates and final products. And then we could successfully apply this reaction scheme to different data sets. So that actually this mechanism was validated. And something interesting that we can also evaluate in this type of modeling is the reaction rate constants. So we can also compare them based on different emulsion properties. And we observe actually some differences in that aspect. But because of time constraints, I cannot show you more results. So if you have any question, please let me know. But I can explain further on this. But more or less, this is a summary of the multi-response modeling process and how you can obtain mechanisms based on chemical reactions that can be generated based on the own data that we produce and on literature. So as final conclusions, in the gastric phase, we could tailor the lipid digestion kinetics by employing emulsion with mixed interfaces. So we mix pectin and twinate at different concentrations. But then in the gastric phase, in the small intestinal phase, excuse me, the modulation of lipid digestion kinetics depended more on the emulsion stability, and especially for these molecular-based emulsifiers. Then about the lipolysis mechanism in the gastric phase, we could obtain and validate this reaction scheme that was obtained via multi-response modeling. Well, this is everything I wanted to show you today. I'm pretty sure that you have several questions, so I'm happy to answer them. But thank you very much for taking your time to listening to me.
Thank you, Marcos, for your nice presentation. Now we have some questions. The first one is, when the emulsions are applied into food products, do you think the droplet size has an important effect on lipid digestion, or do you think that the food matrix has more effect?
Well, thank you very much, Ever, for that question, and thank you for the whole organization team for this kind invitation. About the question, droplet size and food matrix, yeah, it depends. So it depends. Yeah, for sure, all droplet size will have an effect, but it depends also on which type of food matrix we apply this. No, it would be a food matrix which is very simple, or yeah, if it's a highly structured food matrix, then the food matrix will play a major role. Like for example, I'm talking about highly structured ones like oleogels, for example. They really restrict the access of lipases to the oil droplets in some cases. So yeah, in this case, the droplet size plays a minor role, but the highly structured food matrix can take over these properties. So it really depends on the case. If we talk about a more simple food matrix, for example, like milk, or yeah, more simple, yeah, in between brackets, but like a more liquid system, or yeah, a more simple system like milk or a plant-based beverage, for example, then in that case, the oil droplet size could play a major role. But yeah, it depends on the ingredients that we add, on the structures that we form. So it's really depending on that.
Okay, perfect. Thank you. And the second is, why did you choose citrospectin?
Yes, so citrospectin is side stream, first of all. So from the juice industry and some other industries, this is a side stream that is extracted from lemon peels or orange peels. So in our case, in the laboratory where I performed the PhD, this is a lab that investigated pectin very deeply. So that's one of the reasons. But the other reason is mainly because it's a side stream. So we wanted to consider this, let's say, valorization of the pectin, and also we know that this is a novel ingredient, and especially it's a clean label ingredient. And in our lab, we have shown with a lot of with different research that pectin has interfacial activity, so it's able to form emulsions and to keep them stable over the time. And this was also shown in the last part of my PhD, in which we check the interfacial tension kinetics. So pectin is able to absorb to the interface, so to form emulsions and to keep them stable. And I think it has a great potential to be included in emulsions, to be used in emulsions, especially because for companies it's a clean label ingredient, so it doesn't have an E number. So it could be quite interesting for companies to employ it.
Yeah, thank you very much. And we have more. How did you measure the levels of digestin triolein?
Yes. So in my PhD thesis, we quantified different lipolysis products. So we quantified monoglycerides, diglycerides, free fatty acid, and based on these lipolysis products, we estimated the amount of digested triolein. So in this case, we also employed a single fatty acid triglyceride. So I'm talking about triolein. So it's a glycerol attached to 3 oleic acid molecules. And this is because we intended to be as precise as possible with the quantification of lipolysis products. So to have a single peak, so each peak represented only one molecule. So in the HPLC chromatorium. So that's why we use this single fatty acid triglyceride. And so to have a excellent identification, but also quantification of each lipolysis products. And we use this data to estimate the TAG, or the triolein, the digested triolein, let's say.
Okay, Thank you. One more question. I think that we have time. You mentioned that there is potential of pectin to be included in emulsion products. Could you tell more about that?
Yes, so this is linked a bit to the second or third question. So pectin, as I mentioned, is a side stream and it's extracted for these lemon or citrus products pills. And in the team back in the lab where I made did that PhD, we prove so different researchers prove that pectin has interfacial activity and it can be employed in emulsions. And in this case, pectin, because it's a biopolymer, it allows the absorption of lipase. So we can have stable or relatively stable emulsions during digestion that allows lipase absorption. So that's why we chose this molecule also, because it has interesting emulsifying properties, and also it was relatively stable during the gastric phase, especially. So that's why we chose this molecule.
Okay, thank you, Marcos. One more question, maybe.
Yeah, sure.
What kind of oil did you use for the emulsions? And also, do you think the type of oil could affect the lipid digestion too?
Yeah. So we employed triolein. So this is a single fatty acid triglyceride. So it's a 3 oleic acid molecules attached to the glycerol moiety. And we chose that triglyceride as a substrate for lipase, for gastric lipase, because first of all, it allows us a good identification and quantification of lipolysis products, as I mentioned you before, but especially because based on this data that we had of different lipolysis products, we could obtain really mechanistic insights into the lipid digestion phenomena, let's say. So as I mentioned, as we show in the last slide of the lipolysis mechanism, you see that we quantify different lipolysis products, and we could establish this mechanistic model, and we could explain, for example, the specificity of gastric lipase towards the SN2 position, and we could even estimate the rates at which this SN2 position was attacked by the gastric lipase as compared to the other positions. So using single fatty acid triglyceride really help us to obtain these deep insights into the lipolysis mechanism.
Okay, thank you, Marcos.
You're welcome.
And we have 2 more questions. I think that we had time. Yeah. Okay.
Sure.
Can other emulsifiers modify lipolysis instead of that you use the twin AT? This in case to reduce lipolysis, or the pectins to increase the lipolysis?
Yes. So one that would replace twin AT, yeah, because twin AT is also an artificial emulsifier, but in our case we employ it because we could obtain really stable emulsions, but something that could replace twin AT could be, for example, like natural emulsifiers that could replace really twin AT to avoid lipid digestion, especially in the gastric phase, is difficult to find because, for example, lecithins, they also allow lipid digestion. But if we think about other options, I would, for example, refer to pickering particles because they really have a high affinity to absorb to the interface of oil and water emulsions, and they are really difficult to dissolve by lipases. So with these pickering particles, we could form emulsions also that have very low and very slow lipid digestion kinetics. And then molecules, on the other hand, to have very high ones to replace pectin, for example, we could use other other biopolymers. I'm thinking about, for example, proteins, like milk proteins, or even some plant-based proteins. In one of my articles, we also employed soy protein isolate, for example. This could be also an option to replace pectin. But since we saw pectin had some interesting properties, we decided to go for it. And
okay, thank you. And I think that the other question is related. Why modulate lipolysis for lower the levels of the gastric stage? In this case, the twin 80. Could you give us, maybe if possible, if you have an example or an application?
Yes. So actually, what we performed in our research was to really check if we could tailor the lipid digestion kinetics, like obtaining high or low levels. So we didn't intend to have a specific application or purpose for in this case. But if you ask me about obtaining really low lipid digestion levels or slow kinetics, but I'm thinking more about slow kinetics because the rate of kinetics is proven to affect, for example, satiety or some physiological responses like production of satiety hormones and so on. In the gastric phase specifically, there are no studies, so maybe we haven't discovered yet or the link between satiety hormones and digestion in the gastric phase, lipid digestion in the gastric phase. This will maybe come in some years, we don't know. But for example, there has been one satiety hormone identified. I'm talking about ghrelin, which has been hypothetically linked to lipid digestion, but yeah, this needs further research. But now we have established like a emulsified model system that could have different lipolysis kinetics. So maybe in the future, this system could be used also in some applications and so on.
Okay, perfect. Thank you.
Yes, you're welcome.
Yeah, it was last.
Okay, so if there are no more questions, no. Okay, thank you very much, Marcos, for joining us and for presenting your work. I would also like to thank everyone else for attending our 7th Infogest Viva webinar. Before we end this webinar, we would like to thank Talita for all her work organizing the webinars. Talita will be leaving Chagas soon to start a new job. So we want to wish her the best of luck in her new position. We are going to miss her. And finally, we would also like to introduce our next speakers. So the next webinar will be on the 10th of May. So exceptionally, it will not be the first Wednesday of May. It will be the second Wednesday. And it is going to be with Dr. Jin Wang. The following month, we will have a webinar presented by Dr. Jessica Guevara on the first Wednesday of June. And then on the first Wednesday of July, we will have another webinar presented by Dr. Susana Pinho. And we already have a speaker scheduled for the first Wednesday of August, who is Dr. Izuri Jayawardana. So see you all in the next webinar on the 10th of May. And the webinars will also be available on YouTube if you would like to share them or watch them again anytime. Thank you. Bye.